Hello, thank you for joining us. Today, the IEEE Solid-State Circuits Society and tinyML are hosting a joint webinar. The topic of today's webinar is The Intersection of SSCS and AI, A Tale of Two Journeys, presented by Professors Vivienne of MIT and Boris Murmann of Stanford University. Today's webinar will be an hour long. Professor Sze and Murmann will be available to answer any questions at the conclusion of the presentation. Please use the Q&A window on your dashboard to ask your questions. We will address them jointly at the end. Questions will be moderated by SSCS Webinar Chair Alvin Loke. Attendees of this webinar have the opportunity to earn a certificate of participation. We will post a link and details on how to obtain the certificate in the chat window of the dashboard. The webinar slides and video will be posted on the SSCS Resource Center within a week and will be available free of charge. Today is the inaugural webinar launched by SSCS called Webinars for Young Excellence, dedicated to YP members to gain more insight in industrial design practices, collect career advice, present research ideas, and beyond. At the conclusion of this webinar, all registrants will receive a survey. Please fill this out and provide your feedback, especially for future webinar topics. Zeynep Lulic, SSCS Young Professionals Chair, will now talk about this webinar program.
Hello, welcome to our IEEE Solid-State Circuits Society Webinars for Young Excellence program. My name is Zeynep Lulic and I am the SSCS Young Professionals Chair. Young professionals and students are more than 30% of our overall membership, and they are the future of SSCS. As YP members, we are trying to address the different needs and interests of our younger members with initiatives like this webinar series. Our aim is to offer these webinars on a quarterly basis. In the following two slides, I want to talk very briefly about some of the example benefits of SSCS membership for YP members and also a few example activities of the YP committee. As an SSCS YP member, you can access SSCS Resource Center, which contains technical tutorials, short courses, and webinars. You can enjoy distinguished lectures in your local settings. You can apply for travel grants, pre-doctoral achievement award, and circuit design contests. And you can develop leadership skills and make professional connections by becoming a local or global YP leader. Please let us know, or your local section know, if you want to become a YP volunteer. In the next slide, I want to also briefly cover some of the other activities that our committee has been working on. We have recently launched an online mentoring platform. With this platform, you can connect with leading SSCS mentors and mentees from all over the world at your own pace and time. We have been organizing micro-mentoring sessions in SSCS-sponsored conferences over a decade. Recently, as conferences going online, these sessions are also going online. So please stay tuned for our first online mentoring event, co-organized with Electron Devices Society. This online mentoring event will be held next month on June 18th as a part of 2020 VLSI Symposium. And finally, Webinars for Young Excellence program is a new webinar series dedicated but not limited to YP members. This new webinar series complements the monthly SSCS webinar program that focuses on technical tutorials and developments. As part of the Webinars for Young Excellence today, we bring to you the intersection of SSCS and AI, a tale of two journeys. We are organizing this talk together with tinyML community. Now I want to give the floor to Professor Boris Murmann for a few words about tinyML.
Thank you so very much, Zeynep, for the nice introduction. I want to share just a few words about tinyML and what it is about. So the tinyML community was actually formed a couple of years ago, and I was one of the founding members of this organization. This was basically all triggered by this need of ultra-low power machine learning at the edge, and we saw the need of bringing various kinds of researchers together, including industry professionals, academics, and also new people who are interested in the general field. What's somewhat unique about the tinyML community is that we consider hardware as software and the system aspect in parallel. And so this is a very broad community that's trying to benefit from the synergy between these levels of abstraction. So if you're interested in learning more about this, please go to tinyml.org. What you see there is links to various events that we are holding, and most of you will be able to participate in these depending on your location. We have an annual summit in the US, typically in March. We have an event in Asia, typically in Shanghai. And then we also have meetup seminars, and I'm going to show you an example on the next slide. These result in these bi-weekly webcasts. They're also found on YouTube. All of this is free. This is one of the principles of this community. Everything is free and broadly available. Here you can see a preview of the next tinyML talks. This will happen on Thursday, May 28, and you can register at this link below in case you don't want to write this down. Of course, you can find all of this information on our website. So with that, thanks again for tuning in today, and I think Vivienne is next.
Thank you, Professor Murmann. So let's start our webinar. This webinar will be divided into two parts, presented by Professor Vivienne Sze and Professor Boris Murmann. You can use the Q&A section on your dashboard to ask your questions. Please make sure to send your questions to all panelists, and we will address them jointly at the end. Professor Vivienne Sze will be presenting first. Dr. Sze is an associate professor in MIT's Department of Electrical Engineering and Computer Sciences, and she leads the Research Lab of Electronics Energy Efficient Multimedia Systems Research Group. Her group works on computing systems that enable energy-efficient machine learning, computer vision, and video compression processing. She is widely recognized for her leading work in these areas and has received multiple awards in various fields. Professor Sze, the floor is yours.
Great, thank you very much for the introduction. So it's great to be here for this kind of new series on discussing our journeys in research, in particular the focus of and AI. Before I begin, I think just a couple of things. I want to mention that I'll be talking about a whole bunch of work today, and it's actually done in a collaboration with various folks. This is not all done by myself, and this is going to be actually an ongoing theme within the talk today about the importance of crossing boundaries and collaborating. Another thing is that I just want to mention that the slides are also available at this tiny link. The reason I'm pointing out that I'll go through a couple of things, but maybe a little bit quickly in some cases. So if you want to just like follow some of those links or follow the slides at your own pace, you have this available. So as mentioned, by the title, the key interest is how exactly we get into the space of AI. So basically, very broadly speaking, in my research career, I've covered kind of 3 areas-ish, and I'll try to talk about how this journey led to AI, beginning with video compression, then looking at neural nets, and then most recently robotics. What brings all of these challenges together, or applications together, is that they're highly compute intensive, so they have to deal with a growing volume of data that's being processed. The algorithms used to process them are getting increasingly complex in order to improve the quality of results. So for example, in compression, you need to be able to compress better. And in neural nets and robotics, you need higher accuracy. Also in these applications, they often require, from a systems point of view, high throughput and low latency, as well as energy efficiency. So really, in order to meet all of these challenges together, really at the core of it, regardless of the application, I think the thing that ties all of this together is that it's important to look across the entire stack and look at co-designing from an algorithms, architecture, circuits, and systems perspective. All right. So I'm going to start this journey in terms of talking about some of the research that I did back when I was a graduate student at MIT, and then also when I was working at Texas Instruments. And really the theme of that research, or where I started, was looking at compressing pixels. And at the time, this is back before the iPhone when this all started, we were thinking about, how do we make, pixel compression ubiquitous so that all devices have it. The reason we tackled video compression or video in general is because you could arguably say that video is the biggest of the big data. It accounts for over 70% of today's internet traffic. Actually, I would argue in this current situation, probably even more. And of course, there's a lot of increase in applications, content fidelity that's required. So it's really important to compress well. So in fact, if you are going to store or transmit video, you have to compress it. So it's really fundamental in terms of just handling video. Also, in terms of the sizes of the videos, they continue to grow. So we know that screens are getting larger. We also have virtual reality. So there's a lot of video there, but also you often have to do this in real time. So you need to be able to compress quickly as well to keep up with the resolutions and the frame rate. And then, of course, now we know video is a must-have kind of feature on portable devices. But of course, on these particular devices, we know that the battery capacity is not keeping up with demand. Then at the same time, low power and energy efficiency is really key. So the center of the research within my PhD was to kind of address these challenges. You'll see that the challenge is kind of similar in the AI space. And really, this is working in Anantha Chandrakasan's group back at MIT. The focus of his research group was, looking at low power circuit design techniques. And so we were interested in applying them to video compression. And at the time, H.264 was, the state-of-the-art standard and account for 80% of the online content. And one of the key strategies that we used in order to make video compression low power was using voltage scaling. So as you can imagine, as you scale down the supply voltage, the energy consumption goes down. But then you had to combine it with parallelism, because what happens is when you scale down the supply voltage, the delay increases. So to make up with the increase in delay, per operation, you have to do multiple operations in parallel. So for example, rather than taking time t to go do a given operation, if you could, take 2t to do each operation, but then double the number of operations that you had in parallel, you could maintain the same throughput and you can reduce the energy consumption. And so we explored this a lot in conjunction with Daniel Finkelstein, Mahmoud Sinanjo, looking at how do you build video decoders that are super low power that can operate, down at the time we were looking at 0.7 volts for a 60 nanometer process, and still be able to achieve a standard HD at 720p, 30 frames per second at under 2 milliwatts. At the time it was 6 times lower than state of the art. But through this process, these are very nice circuit level design techniques, but through this process we noticed something, which was that fundamentally speaking, as you start looking at more advanced algorithms for video compression, what it fundamentally does is that it removes redundancy in the video, and so as a result it introduces dependencies, and so as a result it becomes much more difficult to parallelize. And of course, if even a certain block in the video codec is hard to parallelize because of Amdahl's law, it's going to limit the overall throughput. And in fact, this indeed was the challenge in the entropy coding engine called the Kabak engine in video compression. And so what we had to do was now we had to move from circuit design to start thinking about, well, can we jointly think about how to redesign the algorithms to make them more hardware friendly itself. So this is like kind of my first experience with the co-design aspect of the entropy coding algorithms with the hardware together. And as a result, we can 10x, over an order of magnitude increase in throughput. But the key challenge here, as you change the algorithm, you have to still make sure that it performs well. In particular, in the video compression, making sure that the coding efficiency, which means how well it compresses, actually is the same, because that's fundamentally the overall goal. This led me to join Texas Instruments after I graduated, and there, just as luck would have it, there was a new video compression standard called high efficiency video coding that was being developed as a successor to H.264. And like every standard, the goal there was to double the compression, meaning that for the same quality image, can I half the amount of storage that I need? But at the same time, what was really interesting with HEVC was that we also had system level requirements. So at the time, this is starting in 2013, we were starting to think, high throughput is really necessary. So you need to maybe go to Ultra HD 8K resolutions or 120 frames per second. And then of course, low power, because back in, when H.264 was developed 2003, that's like pre, video on a phone. Now everybody wants video on a phone. So it's really important to be able to have or double the compression speed, have the storage size, but at the same time not increase energy costs by too much, increase the throughput. So indeed, in the standard, when we developed it, we had a bunch of new tools that we introduced to improve the coding efficiency, but at the same time, we also had to introduce a bunch of new tools to improve the efficiency of implementation as well. And so as a result, it only resulted in about a 50% increase in energy, as opposed to a 4x increase in energy compared to the previous standard. And here was a clear evidence of, even in industry and having an impact, looking at the co-design of both the algorithm and hardware to address the challenges of coding efficiency, throughput, and power consumption. And so the standard body was recognized with an Emmy for this particular work. And now these are, this technology is widely used, in particular if you use any Apple devices using HEVC. Okay, so that was kind of in, pre-returning to MIT as faculty. So when I came back to MIT, I think one of the follow-up questions that we asked was, given this kind of approach, It's one thing to compress pixels, but it's quite another thing to have to understand pixels. And in fact, there's a lot of applications where you don't necessarily want to just watch the video, but you want to understand what the content of the video itself. So kind of the goal of the research when I returned to MIT was, can we make understanding the pixels as ubiquitous as compressing the pixels? Meaning, can we, on every single camera at the back of it, be able to understand the pixels as opposed to just compressing them, which is what we do today. And so, of course, in order to understand the pixels these days, the state-of-the-art approach is going to be, can someone mute themselves? It's going to be using, it's state-of-the-art accuracy, but the challenge here is that when you compare it to something like video compression, it's orders of magnitude going to be more complex. It uses many more operations, a lot of weights to compute, and so on. If we take a deep look, it should be no surprise to all of you that actually what dominates power consumption, if we're really caring about it, particularly at the hardware level, is looking at data movement. So this is a slide from Mark Horowitz, really highlighting, we have multiplications and additions here. And when we compare it to, the energy consumed those for different precision compared to reading memory from even a small 8K-bit SRAM or going off chip and reading from DRAM, you're talking about orders of magnitude higher energy consumption for memory access as compared to compute. So this is something that we can start to solve first from a hardware perspective. In particular, one of the things we looked at is, can we come up with, an efficient hardware architecture that will allow us to reduce the amount of data movement by exploiting data reuse. In particular, can we exploit a lot of reuse at these very small, low-cost memories that you would stick really close to the processing element. And so most of the reads would be in these very small memories, maybe 1 KB memory. And then, of course, as you go farther away or go to larger memory, it's going to be more expensive. So really come up with a way in which you can, change or optimize the ordering at which you do the processing in DNNs to minimize the data movement itself. And resulted in some of the work we did this in collaboration with Joel Emmer, looking at designing efficient, flexible DNN processors. One of these projects was the Iris project, which really focused on coming up with efficient data flows that minimize data movement, and as a result, can achieve an order of magnitude reduction in energy compared to a mobile GPU. So this is the same flavor. So we first start off with the hardware. What's been really interesting in the DNN processor space is actually what we notice is there's been a huge amount of research in this space. And so another kind of question, the obvious question that we kind of asked ourselves, is there a systematic way to compare and explore this space? Because just even trying to understand all the innovation in this space can be quite challenging. So we worked on kind of providing a set of evaluation tools where you can, kind of systematically evaluate different DNN processor design. But it's also what's really important is if you can systematically evaluate it, can you make it fast enough that you can also explore the design space itself? And so in particular, what we're looking at here is looking at kind of evaluating the efficiency of DNN hardware at the architecture level, meaning looking at, given the number of processing elements and the memory hierarchy, can we figure out what the energy cost is, as opposed to going all the way down to an RTL implementation. Another super exciting thing that this enables is it allows us to further bridge other communities. In particular, some of you may be familiar with the fact that in the kind of device and circuits community, we've been looking a lot at in-memory processing or in-memory computing for DNNs. And so this particular framework allows you to do kind of architecture level explorations using these new device technologies that are being developed at, within other research communities. And so this again follows the theme in terms of, if you think about where some of the exciting possibilities are in this place, it's really kind of bridging a lot of the research that's been going on across the various different research communities, trying to make DNN processors more efficient. So this tool itself is open source. It's on the Accelergy website. As it turns out, we also have, so ISCA, which is a computer architecture conference. The conference starts this Friday. It's all virtual. And as it turns out, we're going to be holding a tutorial on this particular tool at ISCA. Again, it's all virtual. So I invite you guys to join. You can just check out the website. There's also a tutorial video up already on that. So from a perspective, but we actually also imagine there's a huge amount of work looking at the algorithms perspective. And we want to kind of bridge algorithms and hardware together. And in fact, within our group, we've been surveying the exciting research that's been going on in this space. So we summarized a lot of these in various tutorials that we did at ISCA, as well as a proceedings paper. So I invite you to visit these if you're interested. But what's been fun about kind of looking across different domains or different research communities from how they approach is that we actually enabled us to identify various limitations to existing approaches. So one of which is when we talk about DNN efficient algorithms, you can loosely categorize efficient algorithms into 3 sets. I'm sure many of you are familiar with this. So one is network pruning, kind of removing some weights, making them sparse. You can have efficient network architectures, and you can also reduce precisions. A lot of this work focuses on reducing the number of max and weights. But if you think from a hardware perspective, what we really care about, or from a systems point of view, we really care about whether or not this translates into energy savings and reduced latency, because that's actually from a systems point of view what you really care about. And in fact, there are challenges of doing this. They're actually not good proxies for that. So this is a plot that was on a Google blog, basically from the Google's mobile vision team, really showing that when you compare latencies and max, that operations or number of max is not a good approximate of latency. For example, for a fixed number of max, you can have a 2x swing in terms of latency, or from a fixed latency, you can have a 3x swing in terms of max, right? Another thing from our own work is that, often people looked at number of weights and said, well, there's few weights, so, it should be energy efficient. But what we really want to highlight is weights alone is not a good metric for energy. On its own, you should also consider all the other data types. So there's also feature map movement as well. And so this is really insight that's garnered from the fact that if you look at the hardware, you can see what are the properties of the DNN that are really affecting energy and latency. And so in this vein, this led to a different kind of thread of the work, which was when you're designing energy efficient models, is there a way to directly integrate these hardware metrics of latency and energy into the algorithm design itself, as opposed to just looking at max and weights, right? So for instance, one line of work was looking at energy aware pruning, where you decide based on its energy consumption, as opposed to in the past, just removing weights that are small. Another line of work, and this is in collaboration with Google's mobile vision team, was NetAdapt, which was basically, can we automate the whole process? So things like neural architecture search are very popular right now, but to drive those algorithms, can we drive it with empirical measurements from the hardware themselves, so latency and energy again? Can you kind of just plug in a platform and then automatically adapt your network for that given platform to maximize or improve, have the maximally beneficial trade-off of, accuracy and throughput, or accuracy and energy consumption? We also wanted to look beyond classification itself. One particular area that we start to ask is, is this going to be useful for applications like depth estimation? Obviously classification is a type of function where you're given an image and you reduce it to one class. You can think of it as a reducing type of thing. But for things like depth estimation, where you want to be given an image and being able to predict the depth of each pixel, that could be considered a much more difficult challenge because you still have to retain a lot of information. And so we want to see if a lot of these approaches applied there. So this led to this fast depth work. And we were able to show that indeed you can get an order of magnitude speed up while still, maintaining the accuracy here. And so in fact, this work we showcased this at ICRA last year, and so we were able to capture some live video and then do real-time depth estimation on a phone for this particular type of work. So this leads to another here, kind of pushing the task in terms of making it more challenging. And so really a higher level question would be, well, a lot of these efficient techniques involve trading off accuracy. So how can we kind of understand what is an acceptable level of accuracy to trade off? And as a result, this leads us to needing to understand the application, because accuracy only makes sense in the context of the application itself. This kind of led us into the robotics, because you can think about, rather than the data set, what I really want to do is, for example, be able to plan my path from point A to point B. In order to do something like autonomous navigation and plan a route, you first have to figure out where you actually are. So robot localization is a very key task there. This is also widely used in AR and VR. And again, what you're trying to do here is that given that video that might be mounted on the robot, as well as maybe some accelerometer and gyroscope in the IMU, can you estimate where the robot is in the 3D space and where it's actually facing? So in this project, the Navion project, we again really looked at co-designing both the algorithms to do this as well as the hardware. And we were able to really drop the power consumption. This is in collaboration with Surtesh Kerman, who's a professor in aeroastro within MIT. And so really, and then the key thing to enable us to do it sticks actually with the theme that we saw before, which was that data movement is very expensive. And so what we had to do here was we had to fully integrate all the compute onto the chip itself. And this required us to apply things like actually low cost compression on the algorithm, exploit sparsity and graph in the linear solver, again, really focusing on packing down and reducing the amount of data movement, the data storage, because from a hardware perspective, we knew that that's what's going to contribute to energy consumption. And then from an algorithm perspective, the challenge was how can we do that without sacrificing accuracy? Another line of work in this space would be looking at robot exploration. So once you figure out where you actually are, how do you decide where you should actually go? If you're trying to explore a completely new space, what you would like to do is try and go to a place where you would get the most amount of new information. And this can be quantified by what we call Shannon's mutual information. So you can see here, tour car here at the bottom driving around, and it's trying to, find as much new information as possible. And it's going to always go towards the bright part of mutual information, because that's where you get the most amount of new information. So we had to, again, do design of this algorithm and this hardware itself to do this. And it allowed us to achieve an order of magnitude or 2 orders of magnitude speed up. I think the key thing I just want to highlight here without going into the details is that in the past, when people use these methods, they could only sample some of the unknown places in the map to explore. Whereas by rethinking about how you do the algorithms and the hardware together, you can actually compute the mutual information of the entire map, and then you can know exactly where to go to get the most amount of new information. I just want to briefly also mention that we've looked at kind of doing this, applying these techniques to the healthcare space as well. So we know that dementia affects millions of people around the world. I think one of the biggest challenges in this particular space is it's actually very time consuming to do these type of assessments. You have to go in to see a specialist, and you have to go through a series of questions that they might ask you. You might have to. Often these assessments are going to be sparse because you can't go in very frequently, once or twice a year, mostly qualitative. So different specialists might different assessments. It's going to have high retest variability. So this is in collaboration with Thomas Helt and Charlie Sodini, who also a lot in the medical space. What we looked at was what's been super exciting is that it turns out that eye movements actually give a quantitative evaluation of the severity and progression of these particular diseases. So for example, you could tell if a certain drug is working or not working. And so this could be a nice complement to the information that you provide to the actual specialist. And so if you can do a lot of this analysis on the phone itself, you could do this in a very cheap way at home, and then you can acquire a lot of different information that you can bring into the specialist. The reason I'm talking about these is that both the healthcare space and the robotics space are really, in these particular cases, accuracy is defined much more deeply than just a classification accuracy on ImageNet, for example. You really have to understand the problem because, for example, here, we really have to be able to have good accuracy in order to assist the physicians in terms of making a decision themselves. And then finally, I think it's really important to consider the entire system. A lot of stuff we talked about there has to deal with compute, but actually often you want to optimize the entire system itself. So one area where that could be relevant is looking at things like depth estimation. Often we need depth estimation for robotics, for AR, VR. Often you can use time of flight where you emit a pulse and then wait for it to come back and tells you how far away an object is. Of course, that's going to be super expensive. So can we think of ways to kind of reduce the cost of emitting the pulse, for example, only emitting it once every so often, or having a duty cycle of it where you emit it once and then you estimate the depth without emitting the pulse in the other time frame. Of course, this depth estimation has to be super lightweight because you're trying to optimize the overall system itself. The estimated one is on the right-hand side, and we're only using the laser, the on time at 11%. Robotics, they can also think of a trade-off between actuation and computing. There's this task called motion planning where you have to figure out, what's the best way to get from point A to point B. Often you want to optimize the shortest path. And often you do a lot of computation to minimize that path. But there's a whole set of robotics out there where the actuation energy and the computing energy is at par. So the key issue here because there's going to be diminishing returns. And so SEEMP, which is like a framework that we've developed, kind of really tries to balance it. Trade-off between computing and actuation. And ideally here, you want to start back at this figure out where this just some of the key takeaways. At the very high level, you can see that all of these examples are trying to illustrate that it's really important to look beyond traditional boundaries, traditional research boundaries. There's a lot of opportunities that lie at the intersection of different areas of research. It's really important to build bridges. And you can apply this co-design approach across different applications, not just AIs, but to the next thing and beyond. And I think it's really important to think of a skill set that's not very, you don't always have to marry like that one particular application, but you want to devise a skill set so that when there's exciting problems, you can apply it to help that problem. And so also looking forward, another question is how to identify, interesting research opportunities, or just, you can imagine like product opportunities as well. The question is here, you first want to ask, is this an important problem? What are the main challenges or bottlenecks to solving this problem? And then you might want to assess what is the skill set needed to address the challenges and the bottlenecks, right? And then do you have the skill sets or not? Or are you excited about learning the skill sets? And so that leads to the other thread of it's always important to be learning and collaborating. And it makes for very interesting research opportunities, but also, allows you to tackle a lot of very interesting problems. People who I collaborate with, who do this type of research, and all of our sponsors, in terms of like some as well. So we recently just completed a book, Deep Neural Network, Efficient Processing for Deep Neural Networks. So if you're interested, I invite you to course. Typically it's held on campus at MIT, but now it's going to be live virtual. So if you're interested in learning for 2 days about this particular topic of how to make designing efficient deep learning systems possible, I invite you to check this out as well. A whole series of talks that we have on both the deep learning side of things and the robotics side of things that are all available also on our YouTube channel. So with that, that concludes my talk. Thank you again for listening. I can pass this back.
Thank you, Professor Z, for the very interesting talk. I want to remind the audience that you can use the Q&A section on your dashboard to ask questions. Please make sure to send your questions to all panelists, and we will address them jointly at the end. Now, Professor Boris Murmann will be presenting the second part. Dr. Murmann is a professor of electrical engineering at Stanford University. His research interests are in mixed-signal integrated circuit design, with special emphasis on sensor interfaces, data converters, and custom circuits for embedded machine learning. He received numerous awards through his career, and he's a fellow of the IEEE. Professor Murmann, the floor is yours.
Thank you, Zeynep, for this nice introduction. So I'm going to talk about my personal story on the intersection of SSCS and AI. And I have to say up front, Vivienne and I did not coordinate. And so you will see some of the interesting commonalities about what we are going to say here. And you will see that I took a little bit of a higher level approach, and I specifically want to answer this question about how can you get involved? And so I want to share with you my personal experience on how that can happen. Let's see. So first of all, for those who don't know me very well, I have always been interested in working somewhere between the physical layer, the physical world, and the digital world. And so I work a lot on sensor interfaces, data converters. But increasingly, I also have to take care of the algorithms because there's great synergy between these three domains. For example, with the algorithms, you can apply various corrections to the raw data that you acquire from these sensors, or you can apply corrections to the hardware that does the digitization and so on. So I know many of the people who dialed in are working exactly in this space. So within this playground, how do I go about finding new problems? And I actually have sort of a very simple recipe. I hope it may be obvious to some of you, but if it's not, it may be refreshing to see. So what is engineering in the first place? So we are all engineers, and the definition really that works the best for me is to say engineering is really design under constraint. So if you want to innovate and if you want to design something new, you have to constantly evaluate the constraints, and you have to find areas where you can identify new opportunities. Where are the constraints changing? What are the new applications, new algorithms, new device technologies, saturations of a trend? So you will find that not all of engineering is moving very quickly. In some areas, the constraints are not changing, and this is where there's little innovation. So you have to actively look for areas where the constraints are changing. And so this is precisely what I have been doing, I would say, throughout my career. And when I go back to around 2012, I was lucky enough to interact with people in computer science, such as Andrew Ng. There are many more who kind of started this whole deep learning revolution that we're in right now. And they kept drawing this very simple chart here that makes a lot of sense. For the longest time, machine learning people have been working with algorithms that rely on human handcrafting of features, and these are labeled here as older algorithms. So in the old days, when we had very little data, it turned out that these algorithms were far superior to deep neural networks, and everyone thought neural networks actually make no sense. But as over time, we accumulated more and more data and had more and more data and also compute available, it turned out that these algorithms that were deemed not so great earlier actually took off and really are ruling the world by now. So right around at this intersection, I would say this is sort of around 2010, 2012, a lot of interesting challenges arose and people stepped up and said, well, look, we need very efficient hardware now to build these systems. We need increasing amounts of memory and so on. And this is where I jumped onto this trend roughly around 2012, 2013, because I saw this huge change in the constraints. So this, of course, is accompanied with this data explosion that you need to make a deep learning efficient. This is actually an interesting chart, especially for someone who's been around for a while. So this is the data number of gigabytes on the y-axis and time on the x-axis. And so really data has been exploding only since about 2010. So before 2010 on this linear scale, it looks like we almost didn't have any data to speak of. And now it just continues to grow exponentially. Most of this is unstructured data. It's emails, it's video, as Vivienne already pointed out, sensor signals. And unstructured means is that just by looking at the raw data, you don't necessarily know what it means, or at least the computer doesn't know what it means. And so we need to go in and make sense of it. So this is what machine learning is about, right? So this is sort of the simplest illustration of what machine learning is. There is data of certain kinds, and here's just a two-dimensional example. Real machine learning data is high dimensional. For example, you could say that an image with 1,000 pixels lives in 1,000-dimensional space. And you want to classify what does this data represent. And so the idea of machine learning is to present many of these inputs along with labels of this data to a machine learning algorithm that then adjusts its weights through a training procedure and then essentially creates non-linearly bounded decision boundaries in this very high dimensional space. This is why you need nonlinearities in neural networks, because these decision boundaries have to have a very tight nonlinear fit around the different classes that you're trying to catch. So this has been taken off and this has been growing massively. So the idea now going forward, you know, as all of these things have already been very successful on servers, the next mission is now to bring them into everyday objects. And the reason for this is manifold. There's concerns about privacy, there's latency issues, and there's just the sheer cost of transporting bits across the internet, which is very expensive. So you want local processing in many applications. Keyword spotting is a very easy example. You want to be able to talk to your device, and the device is supposed to understand you seamlessly. So when you look at what this means, and this makes a connection to tinyML and what tinyML is about, you need to perform a lot of operations per unit in time. So these very successful deep neural networks, some of them require about 10 to the 10 operations, and you want to do that in about 10 milliseconds to look like a real-time operation. And then you want power dissipations no more than, say, 1 or 10 milliwatts. And this gets you in this ballpark where you want to build systems that have about a teraop per second in terms of throughput. And then you want to have that within a milliwatt. So that's about 1,000 tops per watt. Or in other words, if you take the inverse of this, it's about 1 femtojoule per operation. And so if you're someone who knows capacitance and so on, it basically means you can switch about a femtofarad or a little more on a chip per operation. So this sounds incredibly difficult, and it actually is. So if you wonder what the state of the art is, we're probably about 2 orders of magnitude away from this. And so most of what we can do is try to work toward this goal. So this is kind of the guiding star of tinyML, if you want. So what doesn't help is that at present, scaling isn't progressing as quickly as we want, at least not in terms of energy. So this is simply logic gate energy on the y-axis, and the x-axis is feature size. Energy has reduced dramatically when we went down from 65 to say 32 or 20 nanometers, probably around a factor of 8 during that time span. And now as we went from 20 to 7, there's probably only a factor of 2 that we got. So density, of course, still is going pretty strong in technology scaling, and this is why companies invest a lot of money in it. But the simple point here is energy is simply not scaling as it used to. And this has already fueled a trend towards specialized computing and specialized platforms. Everything tends to be customized right now. If you look at, for example, the processors into your phone, they have many accelerators for specialized tasks and so on. And machine learning is really no exception. We're going to have all sorts of accelerators that try to crank out extra efficiency in absence of this coming from the transistors. So this is where I connect to Vivienne's message. The problem is not going to be solved by someone throwing you a slightly better transistor. It's also not entirely solved by just coming up with a better algorithm. We need to work on this entire stack together. So I think of that as this juicy sandwich here. So there's 3 main layers: the algorithms and the software, the hardware and the circuits, and the devices and the materials. And so tinyML is essentially trying to bring this top community together and exploit the synergy. And part of the reason is because the good stuff is really in between, just like on this sandwich. So the innovations really come from considering adjacent areas in this stack. And I think this became very clear in Vivienne's presentation as well. So the point I want to make to the SSCS community here and the SSCS youngsters is that you are actually perfectly positioned. So when you think about this, SSCS is somewhere in the middle of this sandwich. So you are kind of sandwiched between the 2 good stuff layers here. On top, you have the algorithm folks that are innovating really, really fast. I apologize for the small font here, but this is just a simple capture from Jeff Dean's talk at the last ISSCC. He enumerated that there are about 100 new machine learning papers every day. So clearly there are new ideas in this field, and this is where you can intersect. You can try to read, try to digest these form learning study groups. This is what we're doing at Stanford in many ways. Try to find innovative ideas and try to see what you can do as a hardware engineer to implement these. Similarly, the device people are also doing very innovative work these days. There's work toward monolithic 3D integration with extremely dense memory. And this dense memory is basically exactly what machine learning would like to see. We would like to have lots of memory on chip. We would hold something like hundreds of megabytes on a single chip, which is nowadays not possible, at least not for small chips. And so these technologies may enable this, and they may actually influence what kind of algorithms you can have on the chip, and then it will obviously influence how you architect your circuits. So I think the time has never been much better than this within SSCS, at least in machine learning. You can go look up and down and just see on which element you want to innovate here. I want to just give an example. My group published a machine learning processor in 2018 at the ISSCC. And when you look at how that really happened, is it literally came from this top-level inspiration. We saw in 2016 a paper from Joshua Bengio's group that dealt with binarized neural networks and how to train them. This had previously been a big challenge. Nobody really knew how to do this. You need a bunch of tricks. You need batch normalization and estimators for the nonlinearity, straight through estimators. And they figured all of these things out and they said, wow, okay, so now we can build neural networks that you just use binary signals. And we saw this and we said, wow, this would lead to amazingly compact and power efficient hardware. Let's try this out. So about 1.5 years later, we had a piece of hardware that did exactly this. So for us, it didn't even take innovation in the algorithm. We could just borrow this from the high level. And I can only encourage you to do similar things. And by the way, I'm continuously working on this type of thread. Interesting to point out, right? So when you look at this chip that we designed, is this an entirely new idea? So we had this mixed signal processing inside the chip and it looked kind of fancy, but really a lot of these things have been tried before. The key is to do it at the right time when the constraints are right. And so back in the day when my previous advisor did this, Bernhard Boser in 1990, 91, there was not enough data to speak of. The algorithms were not great. People hadn't figured out neural networks very well. The applications weren't well specified. The demands weren't there. CMOS technology was pretty bad. You had a few microns in feature size and so on. And so this pioneering work is very important, but it's important to figure out when is it ripe to actually have an impact. And this is something you should pay attention to. So now with this backdrop, what are the current and future opportunities for mixed signal IC designers? I think Vivienne covered really well what's going on in digital, and the message was also very much related about considering the entire system. And so I want to give a version here for mixed signal IC designers. What are the topics that you can look at and what is somewhat obvious? And so let's look at the typical makeup of these machine learning systems. And so this is specifically an inference system that I'm talking about here. So let me navigate you through this. So in these systems that I'm considering, typically there's a sensor connection, you have audio or images or depth or some other sensor. This information gets digitized. There's typically some pre-processing. And then often comes a deep neural network. And this deep neural network pretty much looks like what Vivienne described earlier. But in addition to this, from a system perspective, you often also want what's called a wake-up classifier. So you don't want to continuously run this very big and powerful network all the time because your sensor data may be sparse and duty cycled. You may not see interesting information all the time. And so these wake-up classifiers are particularly interesting because they have extremely stringent power constraints. For example, for keyword spotting, you typically want to be under a microwatt or so to identify certain keywords, for example, hello Google or something like this, because these classifiers have to be always on, and so you don't want to drain your battery. And so these wake-up classifiers can benefit from analog feature extraction. I'll show that in a moment. Now, even on the deep neural networks, you can benefit from mixed signal skills by trying to sprinkle some mixed signal compute into this processing chain of deep neural networks. And nowadays, this is mainly done in form of in-memory computing, and I want to highlight that as well in a couple of slides down. So let me look more deeply into this always-on wake-up classifier idea. So normally what you would do in a brute force system is you take your sensor information and you digitize it with an A2D, and then you feed this into your machine learning algorithm that gets trained typically with labeled data nowadays, and then you produce some output classes. Now, what this algorithm does is it tries to establish internally some useful features. It tries to figure out that, oh, the edges matter in this, the curvatures matter if I want to recognize humans and so on. And so these algorithms, they learn all of this internally. And this is, in fact, the power of deep learning, that they can adapt these features toward different kinds of problems. But if all you want to do is wake up, you don't necessarily need these fine-tuned completely. And there's an opportunity to go back a little bit in time. And this was sort of the paradigm of the 1990s. How about first extracting some man-made features, for example, gradients. We like gradients in images. And then convert these gradients instead of the individual pixels. And now you have a much simplified machine learning algorithm that can operate on this low dimensional representation of the image and perhaps still recognize pedestrians and so on based on the curvatures and gradients in these images. So this can have a huge impact on power dissipation. And because this operates on analog data, this is very good for solid-state circuit IC designers. Here's an example of something we showed last year at the ISSCC. So my student developed an imager with integrated logarithmic gradient extraction. You see an image of Chris and I at the ISC. This is his poster. Clearly, you can see from this image just two people. You can even see the poster. You can read the poster number, paper number. And so if you present something like this to a machine learning algorithm, it needs to do much, much less grinding to make a coarse classification on whether there's people or other objects in there. Clearly, you're not going to achieve the best performance, but for wake up, this is actually not critical. So now let's go to the in-memory computing problem. So the deep neural networks that Vivienne described basically look like what's on top here. This is the elementary operation. You have some input data. This could be the image or some intermediate feature map. And you're sliding filters across these patches. And as you do this, you want to dot these patches together and sum them up to compute output feature maps. So the way this is done in a digital accelerators is that you have a lot of memory fetches to fetch the filters, the input maps, and then you write the output maps. And it's become a whole science. And Vivienne is really owning that space. On how to do this and how to benefit from data reuse. And this is because, as some architects say, this problem is embarrassingly parallel. There's a lot of operations you can do in parallel. And in the extreme, you can do what I'm showing at the bottom here. You can actually recast this as a weight stationary matrix vector multiplication. So what I mean by this is you can take all the filter weights and dump them into a matrix and now multiply them with the patch that comes into your system. And then you get an output vector that corresponds to these series of output pixels. And so this starts to look like something that has a very regular structure and that is highly parallel. And it avoids this curse of random access in your memories if you now organize this within a piece of memory. So this is the idea of in-memory computing, where you literally create a piece of hardware that looks like this matrix. You broadcast your input data across this matrix. Then you accumulate the results on the bit lines. This is what happens in a dot product within the matrix operation. And then you digitize back, and now you have these output activations for further processing or writing them back, and they may actually go into yet another one of these, and you cycle through this until your neural network is computed. So this is a highly multi-dimensional design problem that is extremely interesting, and many people of this are working on it right now. So there's many options to explore. This can be done with different kinds of memory, SRAM, resistive RAM, phase change, MRAM, and so on. You can accumulate charge or current. There's other ways to do this. You can do partial sums. You can do full sums. And so I view this as an area that is still very wide open for innovation. The design trade-offs are not fully understood. There's a lot of options on whether, again, you do full accumulation on the bit lines or partial accumulation and then additional accumulation in the digital domain. It's not clear how you put this into an architecture in an efficient way. For example, if the kernel sizes are varying. So here's shown an 8x8 operation. But what if my neural network sometimes just needs a 2x2? Does this structure then still run efficiently? The answer is sometimes no. How do you make it reconfigurable? How do you mitigate this overhead? What are the noise requirements on these interface circuits? How to fit them into the pitch? So there's a huge number of questions out there. And clearly the jury is not only out on how to best design these circuits, it's also still out on whether this even makes sense. And so we really need to demonstrate what is possible in this space and then see if it can be adopted in practical systems. So this is, in my mind, really still at the beginning. Now, that said, people have already envisioned how to design larger processors using such a fabric. Here, for example, is a neural network with many layers. And if you have a dense enough memory, you could think about having all the weights stationary and dedicate one array to each layer in your neural network. And the signal would basically ripple between these layers. And you see that this is a residual net. It actually has these forward propagation paths until your final output is computed. So this could, in principle, be very efficient. Whether it's programmable, that remains to be seen. But what is clear that we need very efficient configurable mixed signal fabric to make these tiles a reality. And so far, there is no solution for this that really works to the degree that we want. So this is where emerging memory comes in again. And I have begun to become seriously interested in this because I see basically insatiable demand for huge amounts of memory, and some of the emerging technologies that people are working on deliver this. So here's an example from Max Schulecker's research at MIT and Subhash Mitra at Stanford. They work on monolithic 3D integration, and here what you could do, for example, is have an 8-layer stack of resistive memory. And so really you could get hundreds of megabytes on a chip by doing this, and this could literally be enabling what we just talked about. What's interesting for the analog folks here is that interfacing to these memories is analog. You have to read resistances, you have to program these with analog currents. Making this efficient is an analog problem. That said, it's not only that, it's also sort of how you configure this and make it efficient in the architecture is a huge problem. And so you will have to look left and right and up and down again to really come up with a good solution. So another wide open problem that I want to bring up here that will change everything once we have figured this out is on-device training. So I mentioned this earlier, most of what we do right now is actually still server-assisted training where we have labeled data on a server, we train a model, and then we upload the coefficients to an edge device like your phone. And then these weights or coefficients, they never change. The future will clearly need to go in the direction of making things much more adaptable, and we need to be training on the device. And that will again change everything. It will change all the requirements. It will change what kind of memory you need. It will change what kind of bit resolutions you need. It will change the configuration of all of this hardware. So expect another 10 years of lots of hardware innovation just by this shift from just pure inference to a more agile system that actually does training in the field. And we're really just at the beginning of this. So the algorithm people still haven't really figured out how to do this well. And once they do, you should be in the room and build the first hardware that implements these systems. So how do you succeed? In summary, this is a review of what I said and also what Vivienne said. You need a solid and relatively broad toolkit. You cannot just be someone who knows how to size transistors to participate in a field like machine learning. You need to be open to picking up some system theory, statistics. Linear algebra is the bread and butter of machine learning. You need to be solid broadly in analog and digital IC design. And you want to know something about device technology and what these devices do and how you model them. So at that point, you can really talk intelligently and pick what you work on. Try to be an expert in some area, right? It's fine to be a filter expert, but then don't be afraid to look left and right and accept that there are other interesting things going on and ways you can leverage your in-depth expertise. This is often what we call a T-shaped person or T-shaped engineer. You want to be broad and you want to have at least one area of depth. So this looks like a T. So collaborate, I can only repeat this, Vivienne said this nicely, find good collaborators on the system side, people who own an interesting system problem, or people who own an interesting device technology that you may be able to play with. And lastly, don't get carried away by hype. Don't work on machine learning because your friend is working on this. Work on it because you are interested. And this is especially important because I think I'm not telling you a secret that especially this trend of AI and machine learning is going to come to an end. It's going to be replaced by something else. We don't know what that is. So your skill set must be general enough to cover these future trends and needs. So my last slide, the good news is we're nowhere near done. right? So this is, I don't know if you saw this in the news, this suicidal robot who committed suicide. So this tells you there's actually no sign of AI anywhere near me. If anyone sees artificial intelligence, let me know. In my mind, we're just using this as a buzzword right now. Really, what we do is draw nonlinear decision boundaries in high-dimensional space, which is not the same as intelligence. So there's a lot of things that have to happen in this field to make artificial intelligence actually happen. And circuits and system design will be a huge, huge piece of this, and it will involve many people, including people in the SSCS community. So with that, I want to thank you for attending, and obviously I'm happy to answer questions now. Thank you.
Okay, can everyone hear me?
Yeah.
Okay, great. Okay, well, thank you. Thank you, Boris. This concludes the presentations. So we are a little bit over time, but let's have about 10 minutes for a joint Q&A. So please use the Q&A section of your dashboard to ask Professor Sze and Murmann your questions regarding the content today. And please don't forget to send your questions to all panelists. So we have collected some questions to start. First question. So with communication of bits being so much more energy expensive than processing, I see why one wants to do computing at the edge, yet there's huge processing power and memory in the cloud. Where do you see the future of cloud computing versus edge computing? Vivienne?
Should I take that? Okay. I mean, it depends on the demands of the application. So I guess you could say traditionally, training was happening in the cloud because that's where the data is at, and training is very heavy. And then like inference is happening on the edge. But as Boris pointed out, there's opportunities to perform inference at the edge as well. I think it really is driven by the application itself. So obviously a lot of stuff we both do is looking at the edge in terms of it has benefits of, reduced communication cost, low latency, and more security and privacy. But in the cloud, you also have the added advantage of huge amounts of compute to access huge amounts of data across various different sources. So I think it's a really application-driven thing, and I think they also have very different cost perspectives as well. So I think you can amortize the cost in the cloud a lot as well.
Okay, Boris, any inputs? Your thoughts?
No, I think this covers it, yes.
Okay, next question. Let's see. There's been a lot of interest in analog neuromorphic computing, but analog computing is easily affected by noise. How is this problem solved? What is your opinion on analog neuromorphic computing?
Yeah, this is a very good point. So noise in analog is a very big problem, and so the solution is to go with what's actually happened in digital circuits, which is to regenerate frequently. And this is precisely what happens in this in-memory compute paradigm. You're analog only for a little while, namely on these bit lines. So you go from digital to analog, then you accumulate charges, occurrence on the bit lines, and then you regenerate back to digital. And so this means we don't build a fully flat analog signal where noise just accumulates from layer to layer to layer. We actually regenerate and slice the signal, and this is how VLSI systems work in general. So I personally don't see a fully analog system simply because you need some regenerative blocks in our systems. Now, when you say neuromorphic, the brain does this very nicely with elements that we don't have. We have these regenerative signal processing means with special cells, right, that basically exponentially regenerate the signal. I don't have this fabric in CMOS. I just have copper wires and transistors. And so this is why I think much of the neuromorphic stuff hasn't caught up yet, though it has some merits when it comes to training and so on. But noise accumulation in a fully analog fabric is something that hasn't been figured out how to tame that.
Thank you, Boris. Next question. Can you please share what are the challenges of hardware implementation of deep neural network accelerators that are not yet solved?
Well, I think I was trying to cover at least one of them, which is on-device training. I think this is something that hasn't been solved. Typically for training, you need much higher precision. Nowadays, when you do training, you probably do this with floating point or 16-bit numbers. This would be very hard to do in embedded hardware, and I think that's definitely something to work on.
Okay, Vivienne, your thoughts?
Yeah, so another area I think it's really important, and we all know that when you specialize hardware, you can be much more efficient. But at the same time, given that the workloads continue to change, you also need to be flexible. And I mean, this is forever a challenge in kind of domain specific or specialized hardware. How do you balance flexibility and efficiency in this space? Just because the workloads, like the algorithms are changing so quickly. So how can you design hardware that can quote unquote be future proof, although that would be challenging to do, but still yet be efficient.
Thank you. Question related to quantum computing, about the readiness of quantum computing and applicability to AI and machine learning type problem solving. What are your thoughts?
Vivienne, do you want to take this one?
No, I'm not a quantum computing expert, so I only have to say
neither am I. So quantum computers have their own challenges. We just talked about analog computers. I think quantum computers are analog computers, and they have precisely this issue with noise accumulation. What I recommend you should read is there's a very nice report given out by the National Academy of Engineering, authored by Mark Horowitz. They had a committee to look at the promises of quantum computing, and a lot of these questions are answered in this report.
Okay. Next question. Power and heat has been a significant problem in data-intensive computing. Do you think this could be a complete showstopper for 3D or monolithic or 3D integration?
Oh, no, I think it's an enabler, because a lot of this stuff is dark in a way. I mean, it's memory. It's dense memory. There's actually not a whole lot of heat generated, and because the fabric is so efficient, the heat is also reduced. So I guess when you just extrapolate and use today's metrics and then say, okay, we're going to cram 10 times more on a chip, of course it has to get 10 times more efficient also to be able to get the heat out. But I think this is exactly what should happen in parallel. So I see the concern from a general computing perspective, maybe from a CPU perspective, but not so much from an ML perspective.
Okay. Another question. In embedded ML, will application-specific hardware be more important, or efficient algorithms and software systems going forward?
I would say both. I think, the whole co-design aspect is to allow you to achieve something that neither alone could achieve. So given how aggressively you need to drop the power, I think you need to throw as much as you can to the problem. And I would argue maybe even considering new devices as well.
Okay. Boris, your thoughts?
Yeah, I think this covers it.
Yeah, okay. Another question. Let's see. What would be the interesting research trends to pursue in embedded ML, given Moore's law is approaching its limits? I think somewhat covered this through the discussions already. If you have additional thoughts to this question.
Yeah, I try to highlight a couple of concrete things, right? Looking up on algorithms, looking down on technology, and then monitoring this over time and seeing how the whole in-device training factors in. I think you'll be plenty busy with that.
Okay.
I would also say, I think what's really important is like you need to cross these domains, but not look at them in isolation. I think, the great thing about ML is that everyone's excited about, everyone's working on it. But I think the challenging thing is that they're all in various different communities. And so it's really important to try and, if you really want to make an impact from a device perspective, I think you need to collaborate or think how to move up the stack. If you're, looking at efficient devices, you really need to think about how this would map onto efficient hardware and even new devices. I mean, so, I didn't have time to talk about, but some recent work we were looking at is, all these DNN algorithms have been designed for, digital processors. And then so for circuits and device researchers, they often kind of use those DNN models to benchmark their hardware. But actually, there's a lot of, exciting questions in terms of if I could redesign the algorithm all over again for these particular platforms, how would I do it? And this is something we explored in one of our IEDM papers. And actually, you would approach it very differently because in processing in memory, for example, you have, your weights are super cheap. So for example, maybe you don't want to reduce the number of weights, whereas your, data movement of feature maps can be more expensive. And that's really counter to the trends of how people are designing neural nets for digital hardware. So really really not just taking what, abstraction is good, but at the same time, really understanding what are the implications across the entire stack, or what are the architectural implications? I think Boris highlighted this too, of all the new device and circuits that people are coming up with. What is a way to kind of think and reason about that? And we tried to, that Accelergy stuff is trying to like build a tool to bridge that, but I really would encourage folks to kind of think, across these dimensions, or work with folks across these dimensions to really make sure they're solving the right problem.
Thanks, Vivienne. Okay, another question, and I guess in the interest of time, let's take this as the last question. So minimizing distance to decide, I mean, is important in a robotics problem, but it's also about intelligence required to decide a less risky path. How does a robot consider risk factor in determining the best path, as the shortest distance may be too high risk?
Yeah, I mean, I think that's a great question. In general, in robotics, you have to consider uncertainty, and with uncertainty, you can also consider risk because just your sensors are not perfect. And so part of path planning and exploration is how do you measure that uncertainty? At the same time, I think it's always, okay, so engineering is all about trade-offs, right? So do you spend a lot of time computing to like minimize uncertainty or minimize your path? But then at the end, you don't have enough energy to get there, or, how bad is the risk factor? So it's really, again, looking holistically across the entire system and then optimizing it for there, not just focusing on one aspect or another aspect.
Thanks, Vivienne. Any thoughts, Boris?
No, I think this covers it. Yep.
Okay, great. Okay, well, thank you, Vivienne and Boris, for very, very inspiring presentations, and thank you, attendees, for your participation today. So just as a reminder, this webinar will be posted on the Solid-State Circuits Society Resource Center, as well as the tinyML YouTube channel for future viewing. For future information on future webinars, please visit the SSCS website and tinyML website. Just as a reminder, you will be receiving this a survey after this webinar. So if you can spare a few minutes, please submit your comments. And in particular, we would love to hear from you as far as future topics for this webinar series that might be of interest to the young professional community. Okay, with that said, thanks everyone for your time, and please stay safe and well. Take care.